Hello everyone, hope you're doing well. So in this video, I'd like to give an introduction to related rates, which is going to be an application to calculus to problems or to solving problems that don't look like they obviously contain calculus. And the key idea is that if we have an equation connecting two quantities, then we can differentiate that to get an equation connecting their rates of change. So if we know the rate of change of one quantity, we can calculate the rate of change of the other. So for instance, suppose we have a spherical balloon and we know how much air we're putting into it, then we know how quickly the radius or diameter is increasing. So this will be a simple example. Or suppose we have a ladder that's sliding down a wall and we know how quickly the ladder is sliding down, then we can calculate how quickly the bottom of the ladder is sliding away. And most of the examples we see are going to be relatively simple examples, but you can imagine how these would relate to real world problems, right? Suppose we had a forest fire and we know how quickly the radius of the forest fire is increasing, then you could calculate how much foliage or something like that is being burned up by the fire. So the examples we see are simple ones, but the idea is kind of more widely applicable. Okay, so let's get started. So as we said, if we have an equation that connects different variables, then we're going to be able to differentiate that to find an equation connecting the rates of change. And the tools that we use are going to be pretty much as in the section on implicit differentiation. So let's start with a simple example. Suppose we have a square and each side has length, which is increasing at a rate of 8 centimeters per second. How quickly is the area increasing when the area is 16 centimeters squared? And this is pretty typical of a rates of change or relative rates problem in that we're given a word problem with seemingly no symbols and no calculus in it, and we have to turn it into a calculus problem. So that's also a skill that we need to figure out. So we need to start by figuring out what are the important quantities and what things are changing. What do we need to give symbols to? And we see we're told that the sides of the square have length, which is increasing at some rate. So if we want to study that, we better give a symbol to the sides of the square. So let's call the side lengths x. And okay, we want to know something about the area, so we better give a symbol to that. So let's call it a. So you get to pick the symbols, but try to pick symbols that remind you of what is going on. So x is going to be the side length of the square in centimeters. A is going to be the area in centimeters squared. And we want to then interpret what we're told and what we want to find. So we're told that the length of the sides is increasing at a rate of 8 centimeters per second. So that's going to tell us that dx dt is 8. So here we're differentiating with respect to time because it's increasing at a rate per second. And okay, we want to find how fast the area is increasing when the area is 16. So that's going to be, we want to find dA over dt when a is 16. So we wrote down what we know, we wrote down what we want to find. Our next step is we need to find an equation connecting our different variables. So our variables are a and x. Okay, a is the area of the square, so we know how to calculate the area of the square, right? A is equal to x squared. So this is our equation connecting the different variables. So we've introduced symbols, we've wrote down what we know, what we want to find, we've wrote down an equation. Our next step is to differentiate to get an equation that connects the different rates of change. So we differentiate a equals x squared, and since we're interested in rates of change with respect to time, we're going to differentiate both sides with respect to time. So if we differentiate on the left, the derivative of a is just dA over dt, right, by definition. On the right, remember we're doing implicit differentiation. So if we differentiate a function of x with respect to time, it's going to be the usual derivative, what it would be, which is 2x, but multiplied by dx over dt. So you can either think of it that way, or you can remember, right, it's the chain rule. X is a function of time. So the outside function is u squared. We differentiate, we get 2u evaluated at x. And then we multiply by the derivative of the inside with respect to time. So the derivative of the x is dx over dt. Okay, so now we differentiated. We got an equation which connects dA over dt and dx over dt, which are things we're interested in. And we want to know what happens when a equals 16. So we better plug all that information in. We know that dA over dt is, we know that dx over dt is 8. So we have the dx over dt term. Okay, what do we plug in for x? So we were told that a is 16. So we have to then go back to our equation, a equals x squared. If a is 16, then x is going to be equal to 4. So we're interested in what happens when x equals 4. So let's sub those in. We get dA over dt equals 2. X is 4. dx dt we're told was 8. Okay, we get 64. So we managed to calculate the rate that we wanted, and then we have to interpret that back in terms of words. So we were asked how quickly is the area increasing when the area is 16 centimeters squared. Okay, well, it's increasing at a rate of 64 centimeters squared per second. And remember, the units for derivatives are the units for the top divided by the units for the bottom. So if a was in centimeters squared, t is in seconds, then this is going to be in centimeters squared per second. So this is pretty typical of a related rates problem, right? We're given a word problem. We introduce symbols for the important things. Maybe we draw a picture in complicated settings, but not necessarily in this one. We write down the rates that we know and what we want to find. We write an equation which connects the different variables. We differentiate both sides. That gives an equation connecting the variables where the rates we're interested in. We plug in our information. Maybe we have to go back to the original equation if necessary to figure out what the different symbols are. We find a value for our rate, and then we have to write that back out in terms of words. Okay, so here's the algorithm. So as we just said, we introduce symbols. Maybe we draw a picture. We express our information in terms of those symbols and derivatives of those symbols, so our rates. We write an equation that connects the different quantities. For instance, we had a equals x squared. We differentiate both sides with respect to time or whatever variable is important in the problem. And then we substitute all the information that we had and solve for the rate that we want. And then we should interpret that back in terms of a word problem. So these are always the steps. So we should just try to follow the steps. So let's see another example. So air is pumped into a spherical balloon so that its volume increases at a rate of 100 centimeters cubed per second. We want to know how fast the radius of the balloon is increasing when the diameter is 50 centimeters. So what are the important quantities? What is changing? What are we trying to calculate? Well, we're interested in the volume. So volume is increasing, and we want to know something about when the radius is increasing. So we better give some names to the volume and the radius. All right, we better introduce symbols for those. So let V be the volume and R be the radius. Okay, the volume is in centimeters cubed, the radius is in centimeters. And then, okay, we want to know what do we want to find and what do we know. So we're told that the volume increases at a rate of 100 centimeters cubed per second. So that tells us that dV over dt is 100. And we want to find the rate of change of the radius. So we want to find dr dt when the diameter is 50. So be careful, when the diameter is 50, that's telling us r equals 25. So we want to find dr dt when r equals 25. Now we need an equation which connects the different variables. Okay, it's a spherical balloon, so we know that the volume is 4 over 3 pi r cubed. So this is our equation connecting the different variables. Where does this equation come from? It's going to depend on the context, right? So when we had a square, it was a equals x squared. Here it's going to be v equals 4 over 3 pi r cubed. It's just going to depend on the problem, how the variables are connected. We'll see a problem in a second where we have to use Pythagoras, for instance. Okay, so if we differentiate with respect to time, both sides, we get dv over dt on the left. And then on the right, we have to differentiate with respect to t. And it's just as we did before, right, with implicit differentiation. If we differentiate r cubed with respect to t, we're going to get 3r squared dr dt. So we cancel with a 3 on the bottom. We get 4 pi r squared dr dt. Okay, now we can substitute in the information we know. So we know dv over dt is 100. We know that r is equal to 25. So we plug all that in, and then we have to solve for our unknown, which is dr dt. Okay, so we get dr dt as 1 over 25 pi. And now that we calculated the rate we want, we have to write that back in terms of a word problem. So what were we being asked to do? We were asked to find how fast the radius is increasing when the diameter is 50. Okay, well, it's increasing dr dt, so the radius is increasing at a rate of 1 over 25 pi. Right, so when the diameter is 50, radius is increasing at a rate of 1 over 25 pi centimeters per second. So again, it's the same steps, right? We introduce symbols, maybe draw a picture, though I didn't here. We write down the rate we know, we write down the rate we want to find. Typically, it's at some value of r or x or whatever is happening. We write down our equation connecting the variables. We differentiate both sides, often implicitly, using implicit differentiation or the chain rule. And then we get an equation that connects the rates of change of the different variables. We sub in our different values, and we solve for the required rate. And then at the end, we interpret that back in terms of the original context. So let's look now at a problem with ladders. So these are typically challenging, but if we follow the same steps, we can get through it. So we have a ladder which is 10 feet long, and it rests against a vertical wall. And the bottom of the ladder slides away from the wall at a rate of 1 foot per second. We want to know how fast the top of the ladder is sliding down the wall when the bottom of the ladder is 6 feet from the wall. Okay, so if we don't have any variables or any way to interpret this, it looks like a bit of a mouthful and it's kind of hard to understand what's going on. So here is let's introduce some notation. So we want to know how fast the top of the ladder is sliding down the wall. So we need to have some way to represent the top of the ladder. So let's call the top distance from the top of the ladder from the ground y. And we know something about the bottom of the ladder, how far that is from the wall. So let's call that distance x. Okay, so here is a picture which makes it way simpler. Right, we have a ladder, it's propped up against a wall. The ladder is 10 feet long. The bottom of the ladder is going to be x feet from the wall, and the top of the ladder is going to be y feet from the floor. So here is our notation, and here is our picture. And now we have to write down the rates we know and the rates we want to find, and an equation connecting the different variables. So what do we know? So the bottom of the ladder slides away from the wall at a rate of 1 feet per second. So that is telling us that dx over dt is equal to 1. And we want to calculate how fast the top of the ladder is sliding down the wall, which is dy dt. So we want to find dy dt when the bottom of the ladder is 6 feet from the wall. So in other words, when x equals 60. Okay, so here is what I just said. We know dx dt equals 1, and we want to find dy dt when x equals 6. So this is the rate we know and the rate we want to find. And then, okay, we also need an equation connecting the different variables. So we see from this picture, it's a right angle triangle. Right, here's the right angle on the bottom left. So Pythagoras, x squared plus y squared equals 10 squared. So our equation connecting the variables is x squared plus y squared equals 100. Okay, now we have everything we need. So let's differentiate both sides of this equation with respect to time. So we get 2x dx dt plus 2y dy dt. And then now that we have this equation, we have to sub in all the information we have. So notice the order, right? We first write down our equation, then we differentiate, and then we only sub in after that. So we have to sub in, okay, x equals 6. Okay, well if we first say sub in dx dt is 1, if we sub in the dx over dt equals 1, because that's always the same, we get 2x plus 2y dy dt equals 0. So dy dt is going to be minus x divided by y. So we still have to figure out what x and y to plug in. We're told that we have to plug in x equals 6, but then what y are we supposed to plug in? Okay, and now remember, just like back in one of the previous problems, we can go back and get the other variable from the equation. So we know that x squared plus y squared has to be equal to 100. We know that x is supposed to be equal to 6. So we can use these two facts to calculate y, right? So y has to be equal to 8. So that we have 36 plus 64 equals 100. Okay, now we can plug in x equals 6 and y equals 8. We get dy dt equals minus 3 over 4. And finally, we interpret that. So what did it mean for dy of dt equals minus 3 over 4? So we have a minus sign because y is decreasing, right? Remember, y was the distance of the top of the ladder from the floor. So the negative sign is telling us that y is getting smaller. So the top of the ladder is going down. So the top of the ladder is sliding down the wall, and the rate is 3 over 4 feet per second. Okay, so this was our conclusion. Okay, so we'll do many more examples on this. The more examples we do, the easier it gets, but remember the steps, right? We look at the problem, introduce symbols for the important variables, maybe draw a picture, then we have to write down the rates that we know, the rates that we want to find, write an equation connecting the different variables, differentiate to get an equation connecting the rates of change, sub in everything we know, solve for the rate we want to find, and then interpret that back at the end as a word problem. Okay, thanks everyone. See you soon. Bye-bye.